We dream of crossing the stars, visiting other suns, and turning humanity into a truly cosmic species. But there's an unsettling clash in that fantasy. What if, for very concrete reasons, we never manage to push beyond the limits of our own backyard, the solar system? The idea sounds harsh, especially with forecasts suggesting that in something like 100,000 years, Earth could become inhospitable for us. So, what's the way out? Is there a realistic path to long-term survival and space colonization? It's worth facing the scenario many scientists put on the table. Within a few centuries, the planet could turn into a giant greenhouse, with seas advancing over continents and swallowing entire coastal belts. Picture a future in which metropolises like New York, Rio de Janeiro, and Hong Kong are nothing but memories. Whole populations move inland, epidemics sweep vulnerable regions, ecological chains collapse, and countless species disappear forever. Oceans, as we know them, cease to exist in parts. Iconic islands slip into myth. Hawaii would be just a word in history, and cities migrate to mountain ranges and plateaus we currently consider extreme peaks. If we accept these projections, the urgency to look outward becomes obvious. That's why an American billionaire, Elon Musk, decided to tackle the problem with practical plans and, like it or not, was one of the few to offer a concrete strategy. His thesis is straightforward. If we want to survive, we have to become a multi-planetary civilization. And in comes a bold idea: make Mars more like Earth. The concept has a name and a history: terraforming, and one controversial proposal among several: using controlled nuclear explosions to release water and gases trapped in the polar regions, trying to thicken the atmosphere and warm the planet. NASA officially considers this unfeasible under current conditions. Curiously, almost no one remembers that the agency itself, in the late 1980s, flirted with studies and proposals that brushed up against Martian environmental transformations before the space program shrank due to budget limits, technical setbacks, and tragedies like the space shuttle disasters. The result of that phase was a pullback. The idea of returning to the moon regularly faded. Projects for new spacecraft cooled, and plans to colonize Mars were shelved. Only when Musk arrived with ambition and noise did NASA seem to wake up. And today, both sides are looking to the moon together again. That rapprochement takes shape in the Artemis program. The goal is to establish, within a few years, a continuous human presence in the lunar environment. The division of roles sounds almost natural. NASA leads the scientific arm, while Musk focuses on technological solutions and, why not, future tourist exploration. On the roadmap is a station in lunar orbit that would serve as a staging post for longer journeys, including to Mars. If that moves forward, crewed landings on Mars stop being fiction and become the next logical step. Permanent settlements, autonomous life trials, and local resource production. Even so, Mars isn't the final destination. Sooner or later, the red planet may prove too small, too harsh, or simply insufficient for human ambition. On that day, looking beyond the solar system will feel inevitable. And here, we hit a wall. According to the physics and engineering we have today, crossing our system's boundary is something we simply can't do with conventional spacecraft. Just look at the numbers for a moment. The average distance from Earth to the Sun is 150 million kilometers, one astronomical unit, the basic yardstick of our cosmic neighborhood. From Earth to the Moon, it's about 384,000 kilometers. To Mars, on average, roughly 225 million kilometers, varying with the orbital dance. Take a step farther, and Jupiter is already around 778 million kilometers away. Pluto, approximately 5.9 billion kilometers. And the edge of the heliosphere, the bubble blown by the sun's winds that envelops us, sits at around 100 astronomical units, about 14.96 billion kilometers. Now compare that to what we can do in terms of speed. The fastest object we've ever built, the Parker Solar Probe, reaches peaks near 700,000 kilometers per hour when it dives into the sun's gravitational field. The ships Musk imagines for interplanetary transport sit around 27,000 kilometers per hour. With that technology, the first Martian colonists should spend something like 6 months aboard roomy starships before touching down on the red planet. And as advanced as that may sound, it's still far too slow for the scale of space. A starship approaching the heliosphere's boundary would take well over a century. To reach the nearest neighboring star with a vehicle like that, we're talking millennia. Does that mean the dream of becoming an interstellar species is doomed? Or are we overlooking a crucial detail? The inevitable question, can we go faster than light? With chemical, ion, or classic nuclear engines? No. The uncomfortable conclusion is that with traditional spacecraft, we may never get past the solar system's doorstep in any useful time frame. If we truly want to travel between stars, we need to play with a new deck, technologies that not only accelerate the ship, but bend the table itself. For decades, the warp drive stayed confined to science fiction, but in the 1990s, some researchers decided to pull the idea out of entertainment and do the math. Mexican physicist Miguel Alcubierre presented a mathematical solution showing that, within the equations of general relativity, there could be a theoretical setup in which space-time is compressed in front and expanded behind a bubble, allowing enormous distances to be covered without locally violating the speed of light limit. That's not the same as saying, we can build it tomorrow. The gap between equations and engineering is enormous. Even so, the concept was refined and new variants emerged, all slamming into the same obstacle: absurd energy requirements and an exotic fuel we don't know how to produce. Still, there are those who argue that, in years or decades, we might manipulate the fabric of space-time in ways that sound heretical today, either by toppling laws we took as unquestionable or by formulating broader ones. And why the optimism? Because cosmology is going through a kind of creative crisis. Recent observations, many from the James Webb Space Telescope, have strained established models, pushing physics into a fertile crossroads. Deep paradigm shifts have historically opened doors no one could see before. Perhaps the door to future propulsion is exactly there. Not crossing distances the way you drive down a road, but crumpling the road to shorten it. Not traveling through space, but sliding along a fold that drops us in another point of the universe. To get there, though, our technology has to advance. A lot. It's worth remembering that we've already tried to classify our own technological progress. Russian astronomer Nikolai Kardashev proposed a scale based on how much energy a civilization can access and use. The idea is simple. The more energy available, the greater the capacity to transform the environment, solve problems, raise quality of life, and explore the cosmos. Roughly speaking, Type 1 civilizations are at the beginning of that journey, still dependent on limited sources and unstable environments. That's where we'd be, groping toward sustainability and trying not to self-sabotage. At Type 2, a species would have fully harnessed the energy available in its own stellar system, reaching a level of control and balance far beyond ours. At Type 3, the civilization would draw energy directly from stars on a colossal scale. And extensions of the idea imagine stages in which intelligent beings master matter so deeply they practically rewrite the rules of the game. On those speculative rungs, we're talking about knowing the universe's laws well enough to act as co-creators, generating any conceivable energy source, traveling between dimensions in a possible multiverse. Sophistication on that scale wouldn't even require a body like ours. The very notion of biology could be transcended. And where are we? At the very beginning, trying to climb one step at a time. If we're lucky and collectively wise, we'll move toward a stage where sustainability and global peace are the baseline rather than the exception. Notice how this ties back to the central theme. Faster than light travel, intelligent life beyond Earth, multiverses, and interdimensional transit aren't necessarily absolute impossibilities. They may just be chapters in a book we don't know how to read yet. It all depends on perspective and time. What's unacceptable under our current equations may become trivial once we open new windows in physics. But even if one day we do manage to travel through space-time, it's worth tweaking the mental picture. It wouldn't be flying beyond the solar system's borders the way a ship cuts through the sky. It would be more like using shortcuts of a different kind, exploiting exceptional conditions in alternative dimensions or geometries to go from A to B without traversing every kilometer in between. Practically speaking, the outcome is the same. We get there. Conceptually, it's another way of moving, based on deforming the universe's fabric rather than pushing a machine until it melts. So, back to the opening question. Are we stuck here forever? Not stuck. Limited by current knowledge? Yes. With today's technology, we'll hardly cross our system's threshold in humanly useful times. But that's not a final sentence. It's a snapshot of the present. Every decade, what we know and what we can do changes by an order of magnitude. Our grandparents saw aviation born. Our parents watched the moon landing. We're learning to live in space for increasingly long periods. The path to the stars may not be a straight road, and it might not be a road at all. It could be an origami trick, a shortcut in the cosmic fabric, a physics we don't command yet. Until then, building a solid presence on the moon and Mars isn't an escape. It's training, it's life insurance, it's a lab to test everything still to come. If you like pushing the limits of the possible, from cities on Mars to folds in space, you're in the right place. Subscribe now and turn on the bell so you don't miss the next episodes. Drop a like to help this video travel farther and share it with that friend who loves debating the impossible. And tell me in the comments, which path would you open first? A lunar base, a colony on Mars, or a straight warp to Proxima Centauri or TRAPPIST-1? Thanks for watching, and see you in the next video.